Before we introduce t-distribution, we need to talk a little about the confidence interval. Point estimate for the mean is x bar, the sample mean. This is our best guess. This is our starting point of what the population mean could be, based on the sample of data that we collected. One key component of a confidence interval is standard error. Recall what we have learned from Chapter 7, the sampling distribution. The standard error of x bar is calculated in this way. The sigma is the population standard deviation. N here is sample size. All we needed to figure out the average distance all sample means fell from the true population mean was to know sigma, which is the population standard deviation and the sample size. From the standard error we are going to use for the confidence interval, we have to make a slight change to this formula. The issue is, in almost all real-world situations, we don't know sigma, which is the population standard deviation. So we can think about it. If we have enough information to figure out the population standard deviation, then we should have enough information to figure out the population mean as well. And then there is no need to construct an estimate of the population mean using confidence intervals. Since we don't know the population standard deviation, we need to use new standard error formulas. We don't know sigma, so our best guess of what it could be is to use S, the sample standard deviation. It is extremely important to notice the following. Sigma is the population standard deviation. S is the sample standard deviation. Both of them are standard deviations, but they do not represent the same things. Sigma is the average distance observations for from the mean using the entire population of data. S is the average distance observation from the mean using only the data in the sample. So remember that our sample statistics are going to vary from each sample of data taken. So we talked about this in Chapter 7. So the new formula for standard error will be the SE equals S divided by the square root of sample size. Again, S here is the sample standard deviation. Another key component in confidence interval is called critical values. Now we have an estimate in the place of the parameter. Therefore, we need to account for more error. The amount of error we have to account for will be bigger when the sample size is smaller. It's just like everything else. The smaller the sample size, the more error we need. How do we account for more error by taking into account the number of samples pulled? We use a slightly different distribution to determine our critical value. We use the t-distribution, and it has following properties. The t-distribution is bell-shaped and it is symmetric about 0. The t-distribution has a slightly different shape for each distinct value of the degrees of freedom. The degree of freedom of t-distribution will be the sample size minus 1. The t-distribution has a thinner tails and has more variability than the standard normal distribution. Here is a picture of z-distribution and t-distribution when the sample size is close to 30 and the t-distribution with small sample size. You can see that no matter we have a big sample size or small sample size, the t-distribution is always symmetric on mu equals 0. However, when the sample size is smaller than 30, the t-distribution has what we call heavy tails. It has a larger value than the t-distribution with a larger sample size. With the increase of sample size, the t-distribution will behave more like the z-distribution, which is the standard normal distribution. This is an illustration of a difference in critical value of a z-distribution and a t-distribution. This curve stands for standard normal distribution, and this more flat curve stands for t-distribution. And this is the curve of normal distribution. So we want to find the critical values for the 95% area. From exam 2, we know how to find the critical values. However, the critical values for the t-distribution will be quite different. We also want to find the area to the left equals 2.5%, and the area to the right equals 2.5%. So notice that since the t-distribution is less peaked, it's making the tail fatter or heavier or thinner. So therefore, the critical values are being pushed far away from the mean in order to get the same area in the tails as the normal distribution. So the red vertical line represents the critical values of the z distribution, and this vertical line and this vertical line represents the critical value of t distribution. Now we'll talk about how to determine critical values using the t-table. So first we want to know the degrees of freedoms, which is calculated as the sample size minus 1. It tells you which row to look at. And then we need to figure out the confidence level, either 90% or 95% or 99%. And it tells you which column you need to look at. This is an example from your textbook. You can pause this video and try to do the question by yourself. We want to find the 95% confidence interval for a mean with 5 observations. First, let's calculate the degrees of freedom, which is 5 minus 1 equals 4. And we know that we want to find the 95% confidence interval. Using t-table, we can find that the t value will be 2.776. Now we are looking for the 95% confidence interval for a mean with 15 observations. The degree of freedom will increase, but be calculated as 15 minus 1, and we are still looking for the 95% confidence interval. Using the t-table, which is table B from your textbook, we have the t value equals to 2.145. Notice that the more samples we report from the population, the more peaked the curve, and the closer your critical value will fall to the center of the curve. So the critical value will decrease. To look for the 99% confidence interval for 15 observations, we can calculate the degree of freedom as 15 minus 1. But instead of a 95% confidence interval, we want the 99% confidence interval. Again, use the t-table, we can find the critical value of t distribution, which is 2.977. Notice that the more confident you are, the further away from the center of the curve you have to go to get 0.99 as the area in the middle of the curve. So the critical value increases.